Alright, the next thing I want to talk to you guys about is the central limit theorem. So the whole point of chapter 7 is that instead of talking about just individual samples from a population, now basically we're talking about groups of samples or sample means. So what the central limit theorem says is that if a sample size n is sufficiently large, then the population of all possible sample means is normally distributed. So basically what that means is that although the population itself might not have a normal distribution, it might be skewed left, skewed right, it might be a normal distribution, if your sample size n, or the sample that you take from that population, is large enough, then that is going to follow the normal distribution. And then you end up with a situation where the mean of your sample means is equal to the population mean, and the standard deviation of your sample means is equal to the standard deviation of your population divided by the square root of the sample size. And for this class, when they say sufficiently large enough, we're going to say that is a sample size of 30 or greater. Now, this doesn't make a lot of sense right now, but when we see a couple of examples, hopefully it'll make a little bit more sense. Alright, we're going to go ahead and check out a problem for you guys as homework where you have to apply the central limit theorem. So this is going to be the homework problem is 7.2.22, and it's number 5 from your 9th homework assignment. It says that the population has a mean of 1,450 and a standard deviation of 400, and it's known to be highly skewed to the right. If a random sample of 64 items is selected, what is the probability that the sample mean will be less than 1,550? Alright, so the whole key to this problem is that, although the original distribution is skewed right, because we're taking a random sample of 64 items, which is greater than 30, the central limit theorem applies, and then that is going to follow a normal distribution, or a distribution that looks like that, rather than one that's skewed to the right. So, also then, these conditions hold true. The mean of our sample means is also going to equal the population mean, which is going to be 1,450. And the standard deviation of the sample mean is going to equal the standard deviation of the population divided by the square root of the sample size. So let's go ahead and calculate what that's going to be. So of course the standard deviation of the population is known to be 400 divided by the square root of the sample size. In this case, the sample size is again 64, so it's divided by the root of 64. And we get a standard deviation then of 50. Alright, so what I'm going to do now is I'm just going to go ahead and graph the distribution of sample means when samples of 64 are taken. So once again, the mean is 1,450, so I'm going to go ahead and put 1,450 right here. Now, once again, this is the distribution of sample means when the sample size is 64. And when the sample size is 64, then the standard deviation of the sample means is going to be 50. So one standard deviation above the mean is going to be 1,450 plus 50, or 1,500. Two standard deviations above the mean is going to be 1,550. 3 standard deviations above the mean is going to be 1,600. And let's see, 1 standard deviation below the mean, 1,450. Subtract out 50 is just going to be 1,400. Then 1,350 for 2 standard deviations below. And 1,300 even for 3 standard deviations below. Now, I'm just graphing that out just to kind of show you guys what's going on. What we're asked now is to find the probability that the sample mean will be less than 1,550. So I'm going to go ahead and identify where 1,550 is, and of course that is right here. So the probability that it's going to be less than 1,550 then would relate to the area to the left of this. So what we want to do then is just find that area. Now, the whole idea is that now, although this is normally distributed, there's no table where we can look up the probability of getting an x value of less than 1,550 when the standard deviation is going to be 50. So we basically have to convert it back to the standard normal distribution and figure out a z-score that corresponds with that x value of interest, and then we can look that up. So let's go ahead and figure out what our z-value is that relates to this x value of 1,550. Now, your z-value is just going to be sample mean of interest, subtract out the population mean, divided by the standard deviation of the sample mean. So it's the same, just instead of having, before we just had a plain sample mean, we just had plain x samples, now we have a sample mean. Before we had a standard deviation of the population, now we have the standard deviation of the sample mean. So go ahead and figure out the z-value that corresponds to our x bar value of 1,550. Let's see, our x bar, plug that in, 1,550. Subtract out our population mean, which is given to us as 1,450. And that's all divided by the standard deviation of the sample means, and that's going to be 50. Calculate that out, and that comes out to be a 2. So the z-value that corresponds with our x bar value of 1,550 is going to be a positive 2. So what we need to do now is just find the area to the left of a z-value of a positive 2. Now, to do that, I go ahead and use the chart in the back of your book. And the chart in the back of your book gives you probabilities between 0 and positive z-scores. So what I'm going to do is I'm first going to kind of think about this in two different areas. I'm going to think about this in terms of the area to the left of 0, which in this case would be, of course, well, always that's going to be 0.5 because it's symmetric. And then to calculate this area left over right here, I'm just going to look that up in your z-distribution table. And it says that is 0.4772. So then finally, we can say that the probability of getting an x bar value of 1,550 or less is just going to be the sum of 0.4772 and 0.5, which is 0.9772. So we can say now the probability of getting a sample mean that will be less than 1550 from this population, if a sample of 64 is taken, is 0.9772 or 97.72%. Alright, next problem I want to check out is 7.2.26, which is number 8 from your 9th homework assignment. So what it does is it asks, suppose 9 items are sampled from a normally distributed population with a mean of 116 and a standard deviation of 18. The samples are 114, 142, 180, and so on. And we want to calculate the probability of getting a sample mean less than the mean for those 9 samples. So basically the first thing we need to do is figure out what the sample mean is, or what x bar is. And of course, to do that, we just sum up all these values, divide by however many there are. Some of those values was 1046, and there was, of course, 9 sample values. So we got a sample mean of 116.22. So now basically the question's asking us, if we have a mean of 116 and a standard deviation of 18, what's the probability of, when taking a sample of 9, getting a sample mean of 116.22 or less? And I'm going to erase everything, that way I can show a little bit more work here. Alright, continuing on the same problem here, I just wanted to erase the problem statement, that way I had some room to show some work up on the board here. Once again, we had a population that had a mean of 116. The population had a standard deviation of 18. We took a sample size of 9 from that population, and we got a sample mean of 16.222. The first thing I want to mention is that the problem said that suppose the items are sampled from a normally distributed population. So now, even though we had a sample size that was less than 30, so it doesn't follow the central limit theorem, because the sample was taken from a normally distributed population, we know that those sample means are going to be normally distributed. So first thing I want to do is just show the normal distribution relating to this situation here. So of course, the mean of our sample mean is going to be equal to the population mean, which in this case is 116. Now, that means that our mean is going to, or 116 is going to go right here. Right in the middle. Now to figure out what the standard deviation is of our sample mean, of course, we're just going to use the formula that our standard deviation of the sample mean is equal to the population standard deviation divided by the square root of the sample size. And we're told the population standard deviation is 18, and the sample size in this case was 9. So that comes out to 6. So let's see, one standard deviation above the mean would be 116 plus 6, or 124. One more standard deviation above the mean would be 130. Three standard deviations above the mean would be 136. One standard deviation below the mean would be 110. 2 standard deviations below the mean would be 104. And then 3 standard deviations below the mean would be 98. And let's see, we're asked to determine the probability of getting an x bar value less than 116.22. So let's see, 116 is there, 124 is there, so 116.22 has to fall somewhere about right there. Now, of course, to figure out the probability of getting an x bar value of less than 116, that's going to be the area to the left of that. course, those are all values less than the 116.22. Now, the whole issue is that there is no normal distribution table that has a mean of 116 and a standard deviation of 6. So what we have to do is basically change our x bar interest to a z value of interest. And of course, to do that, we just go ahead and use the formula. The z value is equal to x bar, subtract out the population mean, divided by the standard deviation of the sample mean. So go ahead and plug in our values. Our x bar value is 116.22. Subtract out our mean of 116. And that's all divided by the standard deviation of the sample means, in this case 6. And we end up getting a z value of 0.307, 0.037. So of course that would go somewhere about right here. And we are still interested in finding the area to the left of that. So once again, I'm going to use the table in the back of your book that gives you probabilities or areas between 0 and positive z values. So since we want this entire area, I'm going to kind of split it up into two different areas. The area to the left of 0, or all this area right here, which we know is just going to be 1/2 or 0.5. And then the second area of interest is this little chunk right here between 0 and a positive 0.037. And of course, that's the probability that z is between 0 and 0.037. And your table, it only goes to the nearest hundredth, so I'm going to round that to 0.04. I look up 0.04 in your distribution, and you get a value of 0.0160. So now, I just need to add those two areas, and that's going to be the total area or the probability of getting an x bar value of less than 116.222. So the overall probability, or the probability of getting an x bar value that is less than 116.222, is going to be equal to that area from 0 to negative infinity, or the 0.5, plus that area from 0 to the positive 0.037, which is 0.0160. Add those up and you get 0.5160. And that's the final answer.